welcome back to the workshop. We want to continue taking a look at section 3.5, multivariate distributions. And we're going to start by looking at discrete random variables, and we're going to keep it with just two for now. So let's take a look at our notes. All right, so a joint probability distribution. If x and y are discrete random variables, the function given by f of x is the probability that x is equal to x and y is equal to y for each pair of values x, y within the range of x and y is called the joint probability distribution of x and y. All right. So this is pretty much exactly what we saw previously for a single variable. It's just if we were to ignore this and ignore that, that is exactly the single variable situation, right? So when we look at the two variable situation, we're just adding in this variable here. Again, that's supposed to be an x. Probability that x is x and y is y. So let's take a look first at a very simple example. So let's consider rolling a die and flipping a coin where both are fair. So it's an incredibly uninteresting example, to be honest, but it gives us the basic idea. So again, we're looking at the two variables x and y. So x is the number rolled on the die. The dots on a die, by the way, are called pips. So 1 pip, 2 pip, 3 pips, 4 pips, 5 pips, 6 pips. Cool. Okay, and then let the random variable y be the result of the coin flip. Now, again, this is one where it doesn't have an actual number. So to create a discrete random variable, we want it to be a number. So let's say heads is 0, heads, and tails is 1. Okay, cool. We want to find the joint probability distribution of these two random variables. Now, essentially what happens is we want to find a sample space, or we can find a sample space to help us out. And essentially what it works out to be is if we list all of the possible outcomes, x comma y, then since everything is fair, that means we have equally likely outcomes or equal likelihood. That means all of the possible outcomes have the same likelihood of occurring, the same probability. So what are the possible outcomes? Well, we could, let's see here, for x, those numbers run through 1 through 6. So 1, and y goes between 0 and 1. So 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, 0, and then we also have 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, and 6, 1. So rolling a 3 and a heads, rolling a 5 and a tails, that sort of a thing. But again, these are equal likelihood. So each has probability 1 over n. So we just have to say, well, how many elements are there in this sample space? And there's, let's see, 6 plus 6 is 12, so 1/12 in this case. But these things associate exactly to these cells here. So we get that the probability of rolling a 1 and a heads is 1 and a heads is 1/12. And rolling a 2 and a tails is also 1/12. But that's exactly what it is for each of these possibilities. So this is essentially a uniform joint probability distribution, you could call it. Uniform because the probability doesn't change as we move from one possible outcome to another. So we fill it all in with 1/12, and we call it a day. Okay, so that's our joint probability distribution. So that's a simple example. Let's take a look at a slightly more interesting example. So this is similar to an example that we saw several sections ago. Gosh, I want to say back in chapter 1, we were counting the number of ways to pull textbooks. No, actually, there's a number of ways to arrange textbooks on a shelf. So this is a little bit different, but we're talking about books on a shelf again. So anyway, so on my shelf are, let's say I have 2 programming texts, 1 inorganic chemistry text, and 3 calculus texts. So 2 texts are to be randomly chosen from the shelf. Excellent. 1 for each hand. Pull them out. Let X be the number of programming texts and Y the number of calculus texts. We want to find the joint probability distribution of X and Y. So X, this is the number of, we said, the programming texts, and Y is the number of calculus texts. All right, so again, what's probably the easiest way to go about this is to consider what our sample space actually is. And our sample space doesn't consist of just programming texts and calculus texts. It also includes that inorganic chemistry text as well. So let's say that we have X, comma, Y, comma, Z as our sample space, right? How many of the, let's see, X is programming, how many programming textbooks that I get, how many calculus texts that I get, and then how many inorganic chemistry texts that I get. So we could think of it as, again, programming, calc, and chem. How many of each of those did I obtain? And there's only a few possibilities for this, right? While there's 2 programming texts, 1 inorganic chemistry, and 3 calculus, that means I have 3 possible values here, 2 possible values here, and 4 possible values there, right? Because I could get 0. So 0, 1, or 2 programming texts, 0 or 1 inorganic chemistry, 0, 1, 2, 3, or 4 calculus text, right? But I'm only choosing 2 textbooks. So of course I can't choose all 4 of the calculus, or all 3 of the calculus texts. That doesn't make any sense. So yeah, 0, 0, 1, 2, 3. Anyway, 4 options there. So what I want to do is I just want to run through the ways that I can do this, the number of textbooks that I could pull. That's going to give me 2 textbooks. So let's first say I pull 0 programming texts, 1 calculus, and the chemistry book as well. I could pull 0 programming, 2 calculus, and 0 chem. I could pull 1 programming, 0 calc, and the chemistry textbook. Let's see here, I need just a little bit more room. There we go. Let's see. Okay, I could pull the 1 programming, 1 calculus, and not the chemistry text. I could pull 1, 2, 3, 4. Oh yeah, yep, just 1 more. I could pull 2 programming, no calculus, and no chemistry. And that's the different ways that I can pull 2 textbooks. Excellent. So essentially what we want to do is now we want to use the model of, all right, the probability of this thing occurring is given by the number of ways that that can occur divided by the number of items in the sample space. So what does that look like? Well, I'm pulling 2 books off of the shelf. So I've got 6 books to choose from, 2 programming, 1 inorganic chemistry, and 3 calculus. So I'm taking 6 books and I'm choosing 2 of them. That's how many ways I can do it. Now for this particular situation here, what I'm doing is I'm taking from the 2 programming texts, I'm choosing 0 of them. From the 3 calculus texts, I'm choosing 1 of them. And from the 1 inorganic chemistry text, I'm choosing 1 of them. And that gives me, that's 1, that's 3, that's 1. This is 15, so that gives me 3/15. So 0, 1, 0, 1 gives me 3/15. Notice that 0, 0 is not actually an option here, right? I don't have anywhere that I'm choosing 0 calculus and 0 programming books because I don't have enough inorganic chemistry books to select 2 of them. So this is actually not a possibility right here. There's a couple of different ways that you can handle that. You can either put a line through it and say that can't happen, or you can simply say the probability is 0, and that's fine too. Are there any other possibilities that can't happen? Sure, I can't choose 1 programming text and 2 calculus texts, nor can I choose 2 programming texts and 1 calculus text. And I, of course, can't choose 2 of each. Because 2 plus 1 is 3, 2 plus 2 is 4, 1 plus 2 is 3. So those can't happen. And I don't have enough other books for this to work. All right, so then I've got the, again, the 1, 2, 3, 4, 5 situations that we were just looking at. 1, 2, 3, 4, 5. So let's calculate these probabilities. Again, in this case, I've got 2 programming books. I'm choosing 0 of them. 3 calculus texts, choosing 2 of them. 1 inorganic chemistry, choose 0 of them, divided by the number of ways to choose 2. And this is going to give me 1 times 3 times 1 is again 3 and still over 15. For 1 programming and 0 calculus texts, I'm looking at choosing from 2 of the programming, from 2 of the programming, 1 of them, none of the calculus and the inorganic chemistry. 2 times 1 is 2. Here, I'm choosing from the 2 programming texts, 1 of them, from the 3 calculus texts, 1 of them, and I'm not choosing the inorganic chemistry. 2 times 3 is 6. And here, from the 2 programming texts, I'm choosing both of them, none of the calculus and not the inorganic chemistry. So this gives me 1 times 1 times 1. All right, so then I can take these and fill them into the appropriate spaces. So x is 0, y is 2. X is 0, y is 2. That's 3/15. Let's see here. X is 1, y is 0. That's 2/15. X and y are both 1. That's 6/15. And then finally, 2, x is 2, y is 0 is 1/15. X is 2. All right, 1/15. There we go. Excellent. So this is the distribution of our probability. Of course, we would expect to have one of these occur. So the probability of any one of these things occurring should be 1, because certainly it's going to be one of these things that's occur. That's the only way that I can choose two texts from the shelf. And if we added these up, 2 plus 1 is 3, plus 3 is 6, plus 3 is 12, plus 3 is 15. 15/15, we get a sum of 1 for all the possible probabilities or all the possible situations. So that's our probability, our joint probability distribution for choosing 2 texts from the shelf. Excellent. So that's all that I wanted to share for this video. In the next video, we'll take a look at a theorem for when a function can serve as a joint probability distribution. So I'll see you guys back in the workshop in just a minute.